Hello everyone. Welcome to the next video of Lab 8 of EC 573 Advanced Embedded Logic Design. In the previous video, we discussed about the simple implementation of the matrix multiplication. We analyzed the code and we understood what are the bottlenecks. Now we will focus on the HLS optimization so that we can improve the performance of our code. So in the HLS, when you implement anything on the FPGA, you can implement the architecture serially so that you can take the less resources and but execution time is more. For example, if you see here in this architecture, if you see here, I'm doing the average of an array. So that means I'm going to add all the elements of an array and then I'm going to do the division operation. So serially, it takes a large number of clock cycles, but in terms of the resources, it takes a fewer resources, one multiplier and one adder. Other approach is that I can do all the addition in parallel followed by the multiplication in a single clock cycle by using the parallel architecture, parallel hardware, or the parallel adder unit. So in this case, I need more resources, but my latency is significantly reduced. And in the middle architecture, I have the serial parallel architecture where I can have the some of the compromise on the latency and resources. For example, by using the slightly higher resources compared to the one, I'm going to get the lower latency, and I'm going to use the lower resources than 3 to get the slightly higher latency, but the fewer resources. So my area consumption will be slightly higher, slightly lower than the 3. So this is the hardware software cohesion, or this is how you need to implement the architecture. So the first one uses the fewest resources, like one adder and one multiplier, both constructed from the say logic fabric, that is the FPGA lookup tables, and has a latency of 11 clock cycles. So it is a low throughput architecture. Based upon the target technology, HLS can determine that the 3 addition operation can be scheduled on the per clock cycle by using the logic for fabric, which means it can reduce your latency requirement to the 5 compared to the 11. Then HLS knows that some of the FPGA has the dedicated embedded multiplier and embedded MAC operation like DSP48. So HLS can make use of them to do all the operation in a single clock cycle, okay, and to get the desired performance. But by default, if you don't inform anything to the HLS tool, then HLS will optimize the area. That means it will use the fewer resources as possible. That means it will lead to the architecture 1. The disadvantage of this architecture 1 is that it has a very high latency and low throughput, which is usually not good for most of the practical applications. However, designer can exert the influence by adding the constraints and directives to the HLS code by telling the HLS how to do the scheduling and binding, thus optimizing the code in a better way. So as a designer, when you make use of the HLS, you need to make sure that you get the desired performance by using the directives and the constraint, and you try to reduce the area as less as possible. And here you need to learn about the different pragmas which are there in the HLS. So in the HLS, there are large amount of pragmas are there. So you can make use of these pragmas to get the performance. In this lab, we are going to discuss on these 3 pragmas. One is the HLS pipeline, second is the HLS unroll, and the third is the HLS array partition. These are the most powerful pragmas which are used in the HLS, and this will help you to significantly improve the performance of your matrix multiplication. Okay, now coming back to our matrix multiplication code, which we have discussed in the first video, where we have done the implementation without using any pragma. Now our aim is to how we can improve the performance of your this code. What we got from the first architecture is that we got this statistics that the loop which perform the multiplication, it takes the maximum number of clock cycles. And if you notice clearly here is that in this third loop, which is this one, you are doing the 8 multiplication and the 7 addition. So 8 multiplication plus 7 addition, okay, to get this one. And you are doing it in the for loop, and in each for loop you are doing the, I can say for the simplicity, I can write the 8 addition itself. And in each iteration, so these are divided over the 8 iteration. And in each iteration, you are doing 1 multiplication and 1 addition. And that iteration takes 11 clock cycles. So you have the first 11 clock cycle, then another 11 clock cycle, then another 11 clock cycle. And what you are doing in this 11 clock cycle, in this first clock cycle, you are multiplying the A11 into B11. Suppose we take the first row and the first column. In this clock cycle, you are multiplying the A12 and B21, and then you are doing the addition here. But you can see that in the first implementation, I am waiting for the complete multiplication and addition of the first iteration to start the next iteration. Okay, and that is quite inefficient, right? Suppose if you take the simple example of 3 cross 3. Suppose I take the simple implementation of 3 cross 3, A11, A12, A13. I won't write this part. Then B11, B21, B3. I won't write this part. Now to get the C11, what we are doing? We are doing the A11, B11 in the first iteration. Then we are doing the A12 and B21 in the second iteration. And then we are doing the A13 and B31 in the third iteration. In the second iteration, along with this, we are copying this in the vector result, in the local variable results, and we are doing the A12, B21 plus result. And then here we are doing the, to get the another result one. And then we are doing the A13 plus B31 plus result into B31 plus result to get the final result. So here you can see that all these 3 multiplication operations are independent, right? So why we are waiting for this operation to complete, to perform this operation? Why we are waiting for this operation to complete to start this one? Can't we start the next iteration of the loop 3 as early as possible? Okay, and that is where we can make use of the pipeline pragma. So let's go into the theory of the pipeline pragma. So pipelining allows operation to happen concurrently. Okay, so that means each execution step doesn't have to complete all the operation before it begins the next operation. For example, consider this function which has the each call of the function you perform 3 operations: read, compute, and write. Okay. Now, when you don't do the pipelining, you can see that when you call the function first time, you do the it takes 3 clock cycles to complete. In the first clock cycle, you use the read, second compute, and then write. Then you call the function, your next call gets executed, and you do this one. Now you can see that in the second and the third clock cycle, the hardware used for the read is ideal. When you go through the, when you look at the compute hardware, it is being used only in the 1/3 of the clock cycle. So it is an inefficient use of the hardware. But by using the pipelining, you can see that I can start the read operation of the next function call as soon as possible without waiting for my previous function call to get completed. Obviously, assuming that there is no interdependency between the 2 function calls. So without pipelining, the function in the above example reads the input at every 3 clock cycles, while with pipelining, you can read the input at every 1 clock cycle. That means initiation interval is reduced from 3 to 1. Note that there is no change in the latency of the output. Or latency means when you apply the input, how much clock cycle it takes to provide the output. That latency will not change with the pipelining. Only the how fast you can accept the input or your throughput can be improved. and by making better use of your hardware resources. Also note that here we are not using more hardware resources. We are just making use of them more efficiently. So pipelining is applied to the functions as well as the loops. So for example, here we are talking about the pipelining to the loops. So this is the loop which has the 3 iterations, and in each iteration you do the operation read, compute and write. So when you don't do the pipelining, you will have the first iteration, you complete the first iteration, then you execute the second iteration, then you execute the third iteration. So all the loops are iterations of the loops are executed sequentially. So it takes the 9 clock cycles. But by using the pipelining, you can start the read operation of the next iteration immediately after completing the read operation of the previous iteration. So with this, you can speed up the process, and you can see that with pipelining, your loop execution is completed in 4 clock cycle compared to the 8 clock cycle without the pipeline. So it reduces the initiation interval for a function or loop by allowing the concurrent execution of your operation. So in loop pipelining allows the operation in a loop to be implemented concurrently by using the overlapping of multiple iterations. A pipeline function or loop can process the new input every n clock cycle if the initiation interval is n. If the initiation interval is 1, it can process the new input at every new clock cycle. And the aim of the pipelining to have the initiation interval of 1. So now coming back to our code, what we are going to do is that we are going to pipelining the loop 3 of our code. So in this case, what will happen? Instead of waiting for the addition operation of the previous loop to be completed, I'll start the multiplication operation of the next iteration. So this will help me to speed up the task. Now we will go to the vivado HLS. We will modify our code, and then we analyze what are the improvements we got after we add the pipeline Pragma. Okay, so we will modify the code in the .h file. Again, for the solution 2 also, we are not going to change the type. So we'll have the solution 2. We'll define the solution 2. Now solution 2 will be active. And we'll have the another function here, but with the same interface. Okay, rest, there is no change in the .h file. In the CPP file, again, I'll copy paste the entire function as it is. I'll define this for the solution 2. Okay, and make sure that you change in the project setting, you change the synthesis. In the synthesis setting, you are telling the tool that my now hardware function is matrix mul 2. Then what I'm going to do is that I'm going to go to the loop 3 in my directives. I'm going to say the insert directives. Okay, so I'm going to go to the loop 3, insert directives, and I'm going to do the pipeline and source file and initiation interval. I'll leave it to the tool. Ideally, it should be 1. So now you can see that the tool has added the Pragmas here. Now, another thing is what we want to do is that you want to merge these 2 loops. So one thing you can do is that you can use the HLS loop merge directive, or even if you add the HLS pipeline directive, tool will take care of the merging of the tool. Okay, so either of them you can make use of here. So I'll use it for both the loops here. Okay, so instead of using the pipeline does the same thing. For better clarity, what we'll do is that we'll use the loop flatten one. So it will flat out both the loops. Okay, so we'll add the loop flatten directives.
So for this one, again, you can use the pipeline also. It does the same thing, but loop flatter is the better use pragma here. And for the matrix multiplication, we'll use the loop pipeline. So with this, we are done in this one. What we need to do is that we need to add for the solution 2. Solution 2, I have the matrix 2, and now I'll run the C synthesis. Okay, C synthesis complete. These are the okay. So here you can see that the first and second loop, we were able to get the initiation iteration latency of 1. So our latency has reduced from 80 to 64. The third loop, we were able to reduce it from 6000 so to 2567. And the loop 3, we were able to, actually it has increased it to 192. So we need to figure it out why it has happened. And this is mainly because our iteration latency is 3. Okay, that is something we need to reduce. So whenever you want to reduce the initiation interval, that is iteration latency, either that means we need to add the pipelining pragmas here as well, because here we are suffering not because of the entry and exit of the for loop, because we have now demerged them, but the problem is that we have not pipelining this loop. So it is multiple iterations are not executed as early as possible. So this we need to figure it out. And okay, that we can figure it out quickly by doing this HLS pipeline here, so that we get the initiation interval of 1. So let's see what happens here now. So you can see that now we were able to reduce the initiation interval of the loop, the output loop to, okay, we were able to pipeline the loop 3. We are not able to reduce the initiation latency because it is doing the write operation to the stream interface. So it is still taking the 3 latency. It is mainly because it is doing the read operation from the block RAM. So you generate the addresses in the first clock cycle, you get the data in the second clock cycle, and then you write it over the stream interface. So that's the iteration latency is 3. But you are getting the initiation interval of 1. So that's because you have done the pipelining, and that's why you are able to start every loop in every clock cycle. So you get the total latency of 65 clock cycle. Ideally, it should be 66, but last clock cycle, your data is already available, so it is ignored by the tool. Now, focus on the matrix multiplication loop. Here you can see that the iteration latency is 13 clock cycle. That means each iteration takes 13 clock cycle, and number of iterations are 512, 8 into 8 into 8. But you can see that 512 into 13, you can see that the number is significantly higher than the 2567, because there are each iteration takes 13, and every iteration every number of iterations are 512. So ideally this number should be 512 into 13, but you can see that around 6K, but this you can see that this number is significantly less. Why this has happened? Because we have pipelined the this loop, which means your iterations are started much faster. You don't need to wait for 13 clock cycle to start the next iteration. You are starting the iteration at every 5 clock cycle because your initiation interval is 5. And now we need to understand why the initiation interval is 5. Okay, that we need to understand. Another thing we need to understand that our resource utilization number of DSPs are still same as the previous case. That means we have not done the parallelism of the architecture. We are just doing the pipelining of the architecture. Now we'll go to the PPT and understand the corresponding and these numbers in more detail. Okay, so we have implemented this code. You can see that our resource utilization, if you look at the resource utilization numbers, here, if I focus on the DSP, you can see that it is still 5. So no parallelism of the operation. Block RAM is still the same. No issue. You can see that there is a slight increase in the flip-flop because we are using the pipelining. So you need a internal register to store the intermediate data. So number of flip-flops are increased. And there is a slight increase in the utilization of the lookup table because of the additional logic. And we are also merging the row and column loops. So you need to do the slightly arithmetic to find out the appropriate index. So that's why there is a slight increase in the lookup table, because lookup tables are used to implement the arithmetic operation inside the FPGA. Now, if you look at these numbers, now you can see that the time required to perform the operation in each clock cycle is slightly increased, but as long as it is less than 8.75, we are fine. The number of clock cycles or latency has been reduced significantly from 6148 to 2748. And this has happened because of the multiple reasons. We have merged this loop, so those two entry and exit clock cycles are reduced. So there are 8 iterations, 8 into 2, 16. So 18 minus 16, you get the 64. Same for the second loop. And you can see that for the third loop, we have been able to reduce it from 208 to 65. Though the iteration latency is still 3, so exit and entry are reduced, and by merging it, we were able to further reduce the number of clock cycles. Now, let's focus on this part. We are able to reduce it from 5776 to 2567. So you can see that here we have the 512 iteration. Each iteration takes 13. If you do the arithmetic, in this case, you get the around 6656 clock cycles. If you take the 512 iterations, and it takes the 13, you can see the 13 iteration for every 13 clock cycle for every iteration. But your number is 2567. Why it is happening? Because you have the 5212 iteration. Each iteration you are starting at every 5 clock cycle. So it comes out to be 2560. Okay. So at the 2560 clock cycle, you will start, you are going to start every, you are going to start your 513 iterations. Okay. That will be start at 2560. So your 512th iteration will be starting at 2555. And then that iterations, if you look at the numbers, and that iterations will take the 13 clock cycles. So you will get around the 2568, but you can see that the last clock cycle we ignored because it is the data is available, and we are just going to perform the right operation. So that the total iterations are the 2567. So because of the initiation interval, you are starting your iterations as early without waiting for the previous iteration to complete. You are able to get the faster speed. Now we need to understand why the initiation interval is 5 and why not it is 6, 7, or so on. So let's go into the more detail. So as we know that you can see that initially you are doing the in the matrix multiplication, you are reading the data from the memory, then you are doing the multiplication, then you are doing the addition operation, and then you are writing the data back to the memory. So in that case, if you go to the HLS, you will get the how much time it takes to perform the each operation. So if by using the analysis, okay, so based upon the analysis you got it from the HLS analysis window, you will know that usually the read operation of A and B, it takes 3 clock cycles. So if I start it here, you can see that my read operation will take the 3 clock cycles. So my A11 and B11 will be available at this point. Then you can see that the multiplication takes 4 clock cycles here. So you can see that the 4 clock cycle, I'll get the A11 into B11. And then you can see that I'll take the addition operation that takes 5 clock cycle. So I'll use this one. So result is available at this point 1, and then I take the 1 clock cycle, if I'm not wrong, 1 clock cycle to get the output. So if I see, these are the 5 clock cycles, these are the 4 clock cycles, these are the 3 clock cycles, and this is 1 clock cycle. So totals are 13 clock cycle for every iteration. Now assume that I want an initiation interval of 1. Okay. So in that case, what I'm going to do is that I'm going to start the reading of the next one at this point. So that means here I'll get the A12 and B21. Okay, that is will be available at this point. Then I'm going to do the multiplication. So I'm going to have the multiplication at, I'll take 4 clock cycles. So I'll have the multiplication here. So A12 into B21. Then I'm going to do the addition. Now I need to do the addition with this result. Can I start the addition before I start this result is available? No. So I have to wait till this time, and then I can perform the corresponding addition here. Okay. So instead of waiting here, that means instead of starting the addition multiplication here, I can delay the getting the input data from my loop. So from my input. So what I am doing is that because of this wait, because there is a dependency on the result, I will make sure that my data, which is multiplication data, is available at this point. So to make the result multiplication data available on this point, I'll start the multiplication at 4 clock cycle before. So I'll have the A12 into the B21 available at this point. And to make sure that I have the multiplication available at this point, I will start the reading operation at this point. So I'll read the A12 and A21 at this point, and you can see that there is a 1, 2, 3, 4, 5. That's the initiation interval of 5. So this is how the tool calculates the initiation interval, so that your dependency on the previous iteration is sorted. If you don't have the dependency on the previous iteration, then you can take the data as fast as possible, because here we need to add the multiplication output to the result of the addition output of the previous iteration. There is a dependency. That's why I am not able to have the initiation interval of 1. I have got the initiation interval of 5. Okay. So this completes the second version of the optimized one. In the subsequent video, we will discuss the how we can optimize this code further.